So previously, after defining the notion of divisors, we have constructed two groups, right? One is the group of Will divisors up to linear equivalence, and then the group of Cartier divisors up to linear equivalence. Remember that these are isomorphic if X is smooth, because in that case, every codimension 1 subvariety has a local equation. But they might not be isomorphic in general. Now in this video, we're going to talk about another notion of equivalence that we can put on the divisors, so it's called algebraic equivalence, and from this, we can get another group called the Néron-Savary group. It turns out to be finitely generated, and its rank is called the Picard number. That is another important invariant. Alright, so let's motivate the definition of algebraic equivalence. Now, algebraic equivalence is the algebraic version of the notion of homological equivalence on divisor, so let's discuss that. If X is a complex surface, then we can view its divisors as homology classes as follows. Let's start first with, say, just a curve in X. Well, how do we view this as a two-cycle? Well, a natural idea is just to look at the complex points of C, right? And then we triangulate it into simplices and then choose an orientation, and that turns the complex points of C into a two-dimensional cycle. Now, what's the problem with that? Well, the problem is that C might not be orientable, right? That happens precisely when it's not smooth, because a smooth complex manifold is always orientable. So then instead we want to look at the normalization of C. That's going to be a smooth projective curve, so its complex points are going to form a compact oriented surface. So we can push forward the triangulation and orientation from this normalization to C. This turns the complex points of C into a two-dimensional cycle on the complex points of X. Alright, so that's how we could view a curve on X as a two-dimensional cycle. Right, and now how about a divisor? Well, we just extend this definition then linearly. If we write this cycle corresponding to C by this notation, then the cycle corresponding to D will just be defined as this linear combination. Now, before moving on to define algebraic equivalence, we want to make a remark. We claim that this map is a generalization of the degree map on divisors. Do you see why? Well, let's look at the case when X is a curve. Then every prime divisor is just a point, right? And then we can view them as zero cycle. But this group is just isomorphic to Z, because X is connected. So then this map turns out to just be the degree map. Alright, so now coming back to the case when X is a surface, we have given a way to view Will divisor as second homology classes. This allows us to define a notion of homological equivalence on Will divisors. So two Will divisors are homologically equivalent if they are equivalent as homology classes. However, this notion would only work for surfaces over C. However, this is algebraic geometry and not analytic geometry, so we want to work with other fields too. We don't just want to work with a complex number. Thus, we want to generalize the notion of equivalence here to something broader that would work for other fields too. Thus, in the next episode, we'll talk about algebraic equivalence.